what can be said about the convergence of the following sum? 0 to infinity, 1 over 3 plus sine of k to the power k by use of the comparison test. There's converges by comparison with 1 over 2 to the k, diverges by comparison with 1 over 2 to the k, converges by comparison with 1 over 4 to the k, diverges by comparison with 1 over 4 to the k, and, of course, an option that the comparison test is inconclusive for this sum. Sometimes it's not the right test. There's lots of tests. So, do we have an answer? Is it C? No, but it's very tempting C. We'll talk about why C is tempting.
Is it A?
Is it A? It is A. Converges by comparison with 1 over 2 to the k. Now, what happens? Well, this sine of k is annoying. And the reason it's annoying is it moves up and down. So we don't want that. So we'd like to somehow get rid of it. So we say, well, we understand that sine of k is bounded from -1 to +1. So that says something about 3 plus sine of k. It has to be between 2 and 4. So now we flip everything, and you have to be a little bit careful here. When you flip, you have to reverse the inequality. So the reason that the 2 and the 4 went there was I was technically reversing the inequalities. So 1 over 4 to the k is less than or equal to 1 over 3 plus sine of k to the power k is less than or equal to 1 over 2 to the k. Now the nice thing is that the sums on both ends are converging sums. They're both geometric sums, and we love geometric sums. That's going to be the theme for today, is we love geometric sums. And they both converge, so we say, great. But now the question is, which side do we compare to? Well, if I want something to converge, should I try to be bounding it above or below? What's the intuition? You want to bound it by above. I like to use the words small and big. Small for converge, big for diverge. If I want to show something is small, I have to put it below something small. So I have to put it below something which converges. If I want to show something diverges, I have to put it above something which diverges. So if I want something to be big, I have to make sure it's bigger than a big thing. Now, 1 over 4 to the k converges, but because it's below this sum, I can't make a conclusion. Being above a small thing does not automatically make you small. It's inconclusive. So it's true, 1 over 4 to the k is very tempting, but because of the relationship of 1 over 4 to the k with the sum, it doesn't help us make the conclusion that we want. All right, any questions? Okay. Well, on to today's thought. Bit philosophical. To understand is to perceive patterns. And that's one of the things that's challenging about math in general, but I think about this part of the calculus sequence, is that you have to learn to recognize the right kind of patterns. How do you know what to use, when to use it? And so that's one of the reasons we want you to practice. Practice is a lot about pattern matching training. The more that you practice, the more examples that you see, the better that you get at spotting patterns. And the better that you get at spotting patterns, then the better that you'll do in figuring out what's going on. So think about what's going on. Think about patterns. How do you spot them? How do you use them? Now, what's the goals for today? Well, we're going to talk about 2 more tests. The ratio test and the root test. And what's going on? Well, I'll just sort of jump to the chase. there's sort of a underlying philosophy that says if you were a geometric series, then what kind of geometric series would you be? That's what we're asking. You probably have been in some situations before where people have asked, if you were a kitchen utensil, what kind of kitchen utensil would you be? And that's what we're going to do. We're saying, look, we're going to look at series, and we want to say, how do you behave if you were a geometric series? Now, how do geometric series work? Well, they look like the sum of something to a power. So there's this quantity called rho, and what we'll do is we'll look at these expressions in both these cases. Say, okay, the root test, look at consecutive terms. And what happens to it as you go to infinity? Ratio test, look at the ratio of consecutive terms. Root test, look at the nth root. Now, if they were actually geometric series, what we would get is that multiplying factor. But if we get something else, if it's not a geometric series, maybe we get a number. That number is basically saying, I behave like a geometric series with this value rho. And now we say, if we're less than 1, this is like a geometric series with a very small number, that's going to converge. If we're bigger than 1, it's like a geometric series with a big number, which means that the individual terms are blowing up, that's going to diverge. And so we can figure out convergence or divergence. And these are very important tests. I'd also like to note that they show up in the formula sheet. So they're here in the lower left corner. So you have your limits, your nth roots, and your ratios. And then you say, if it's less than 1, it converges. If it's bigger than 1, it diverges. And of course, if it's equal to 1, more work. And that'll happen. All right, so that's where we're going. That's our goal for today. A quick recap, just to say where we're at. We're building up our convergence test. Here's what we have so far. We have our nth term test. Just says, if the terms get big, it will not converge. The integral test says, hey, if I can treat this like an integrable function, the integral and the sum will both converge or both diverge. The basic comparison test, which says, okay, I can compare this to something. If I'm below something which converges, I converge. If I'm above something which diverges, I diverge. We have the limit comparison test, which says, look at rates of growth. And then you can say, okay, do they have the same rate of growth? If they do, then they both converge or they both diverge. And now we're adding the ratio test and the root test. This is a lot of tests, and we're going to add one more to this list on Monday. The good news is Monday we'll finish it up, and then we'll be able to fit it all on one page. One of the things you want to be able to do is know which test to use when. And I wish I could say, it's going to be totally obvious. But there are certain clues that show up. We'll get some practice with that next week. All right, so let's get into today. We'll start with the ratio test. And word of warning, there's going to be a lot here on this slide, but just focus on the upper left corner for now. So we're taking the limit of the ratio, the next term in the series divided by the current term. And we say, well, what happens to this? If it's less than 1, we converge. If it's equal to 1, there's no conclusion. If it's bigger than 1, we diverge. And we diverge for a very good reason. So let's go through the 3 cases. That's what's happening here. We're going to go through each of these 3 cases and explain what's going on. So what's going on if we're less than 1? Well, if we're less than 1, here's 1. We're below 1. And what we can do is we can say, well, I can go somewhere in between rho and 1. There's this rho plus a little bit, epsilon. So I have some cushion. So I have some space, so I can squeeze a number in between. And to say that rho is the limit says, well, if you're large in n, you have to be close to rho. Which means if we're large, we can't be over here. We have to be near here. So we have to be below rho plus epsilon. And so what does that tell us? Well, it tells us after a certain point, if I want to get to the next term, I'm going to multiply by something that's at most rho plus epsilon of the current term. And once I've reached that point, well, that says if I want to go one term, I multiply by at most rho plus epsilon. If I want to go two terms, multiply by at most rho plus epsilon squared. If I want to go three terms, at most rho plus epsilon cubed, because each step is at most rho plus epsilon bigger. So if I want to go k terms past this point where I'm small, then an plus k is less than or equal to rho plus epsilon to the k a sub n. Now, what does this look like? Well, it looks like an initial piece, which is fixed, and then something to the power k. And that something is smaller than 1. That's geometric. So we're bounding it by a geometric thing. We're bounding it by a converging geometric thing. And so, since we're bounding it above by something convergent, it must also be convergent. And that's the comparison test. So that's why if your limit is less than 1, you converge. Now, what happens if you're bigger than 1? All right, now we move up to this corner. So if we're bigger than 1, we're to the right of 1. We have some space. We can find some small epsilon, call it rho minus epsilon. That's in between. And then we say, well, if we're far enough out, then again, we have to be near rho, which means we're above rho minus epsilon. And at that point, what that means is we're going to grow at least by rho minus epsilon at every stage. But rho minus epsilon is above 1. So when I multiply by rho minus epsilon, I'm getting bigger. So I'm getting bigger and bigger and bigger. So as we head off to infinity, our terms get arbitrarily large. So this is failing the nth term test. The terms don't go to 0. The sum must diverge. Rho equals 1. Why is it ambiguous? Well, essentially it's ambiguous because there are some sums which will converge and have rho equals 1, and there are some sums which will diverge and has rho equals 1. We don't have some space on either side of 1. Because that's what we used advantage of here. We said, well, if we're below 1 or we're above 1, we have some space. But if we're exactly 1, there's no space. And what's the series? The p-series. If you take the ratio, then what happens, regardless of your choice of p, you always get 1 in the limit. But we know that some p-series converge. So, for example, 1 over n squared, that converges. Some p-series diverge. For example, 1 over square root of n. And so that's why there's ambiguity. That's why we need the more work. Now, one thing I do want to point out, and let me pull back this page, because there is something important here. These tests all involve limits. The ratio test, the root test, and the limit comparison test. The limit comparison test, we're comparing two series. Whereas the ratio test and root test is we're comparing one series with itself. But there's one thing in particular I want to point out. In the limit comparison test, we just want a limit. We don't care about the value. But in the ratio and the root test, we do want a limit, but we care about the value. So we, in particular, really want to say, how is it in relationship to 1? For the limit comparison test, we don't care if the number is 1, a half, a million. As long as it's any number, we're good to go. So there's some differences. Make sure you know the differences. All right, so that's the idea. Now, in practice, ratio test is not the easiest test to use, and it's one that we won't use very often, with one exception. I would say. More or less, the ratio test and root test are almost interchangeable, but there is one case when you definitely want to go with the ratio test, and that is factorials. If you see factorials, and remember that's exclamation, so it's not just n, it's n, it's like, very excited. When you see factorials, ratio test should jump into your mind. All right, so here's a question. I think this came from a recent exam. Determine if the sum 1 to infinity n plus 1 times n to the n over n factorial 3 to the n converges. All right. Before we begin, any thoughts? Yes, no, maybe? Well, not so clear. So we got to figure it out. All right, so we look at this. This is our a sub n. And now what we're going to do is, because we see factorial, we need to do a ratio test. One other thing, sorry, I keep jumping back. We put absolute values here in preparation for what's coming, starting next week. Oftentimes you don't need to worry about it. In this case, we don't need to worry about it because everything's positive. So let's look at the ratio. So most of this test is just computing. And then we get to make a conclusion. So rho is the limit. N goes to infinity. A n plus 1 over a n. All right, so let's talk about what is a n plus 1. So we were told, or rather we read it off, a n is the term. N plus 1 times n to the n over n factorial 3 to the n. How do you find a n plus 1? What do you do? What do you do? Okay, plug in n plus 1 where? Yeah, everywhere. See, where there's an n, you put an n plus 1. So everywhere where you currently see an n, put in n plus 1. So this becomes n plus 1 plus 1, n plus 1 to the power n plus 1, divide by n plus 1 factorial, 3 to the n plus 1. So that's how you find a n plus 1. Everywhere where you currently see an n, in goes an n plus 1. All right. So this is going to become a limit as n goes to infinity of, so I'll start with a n plus 1. So n plus 1 also goes by the name n plus 2. Then you have n plus 1 to the power n plus 1. And now you have n plus 1 factorial. And you have 3 to the n plus 1. So this is our a n plus 1. And now we're going to divide by a n. But the thing is, a n is a fraction. If I want to divide by a n, that's the same as multiplying by the reciprocal. Yeah, good, good. So we're going to take a n and flip it. And so we're going to get n factorial, 3 to the n. Then downstairs in n plus 1, n to the n. All right. Nice. So here's our a n plus 1, our 1 over a n. Okay. What should we do next? Yes, we can do some quiet meditation. But of course, on an exam, we only have 75 minutes. So we don't want to do 75 minutes of quiet meditation. What's our goal? What are we trying to do? We're trying to take this limit. How do you take limits? Simplify. I love that. That's almost all of math, is simplify. So we're looking for, in particular, cancellations that can happen. So now let's talk about why did we say this? Why factorials work so well with the ratio test? Well, let's think about n plus 1 factorial. Now, n plus 1 factorial, just think in general in factorials, means you're starting at n plus 1 and you start multiplying. So you have n plus 1, then you have n, then you have n minus 1, dot, dot, dot. Okay, so if you write this out, it's the product of a lot of things. N plus 1 times n minus 1 times all the way down to the end. But what do you see there? It's n factorial. So when you have a factorial, one thing you can do is you can pull off the first term. In fact, you can pull off a couple of terms if you want, and then what's left is the factorial. So that's why the ratio test will work very well. So we say, okay, let's use that here, because I have an n factorial here. So if I want to cancel, I'd really want to compare an n factorial and an n factorial to get cancellation. So we have our limit. N goes to infinity. We'll write some things down. We have an n plus 2. Now, here I have n plus 1, n plus 1 to the n plus 1. Here I have an n to the n. I'm going to pull off an n plus 1 from that term. And now I have n plus 1 to the n power left. Then I have an n factorial and a 3 to the n. And downstairs we have an n plus 1 times n factorial. 3 to the power n plus 1. What's another way to write that? Thinking ahead to canceling. Because I have a 3 to the n. What's another way to write 3 to the n plus 1? It's 3 to the n, 3 to the 1. Yes? Okay, then we have an n plus 1. Then we have an n to the n. What cancels at this stage? Three n factorial, n plus 1, n plus 1. Cool. We're doing great. So that's a lot of cancellation. Now, we have A3 here. And that's a constant. We can bring it out in front if we want. Constants can come out of limits. Then we have an n plus 2 and an n plus 1. We'll put those together. And now we have something to the n, something to the n. We'll put those together. I feel we're getting near the end. I hope. Is there another way to write n plus 1 divided by n to the nth power? Okay, this is the same as 1 plus 1 over n to the nth power. That may or may not be helpful, although yet I wrote it down, which suggests it might be helpful. N plus 2 divided by n plus 1. N goes to infinity. What happens and why? Let's start with the what happens. N plus 2 divided by n plus 1 does what? Goes to 1. Goes to 1. Why? Well, there's a couple ways to argue it. One simple way is, oh, it's polynomial over polynomial. Look at the leading terms. Leading terms dominate. So it's really like n over n. So that becomes 1. Now, 1 plus 1 over n to the nth power, what happens to that as n goes to infinity? And why? How do we know that? Not quite e to the n, but I like that attitude. Goes to e. There's this formula on the formula sheet. 1 plus something over n to the nth power goes to e to the something. In this case, our something is 1. So this goes to e. All right, which means that our row, we have the 1/3 times 1 times e, so we get e over 3. Okay, so we have a limit. Nice. What do we do next?
Compare it to 1.
We what?
Compare it to 1.
Compare it to 1, yes. So remember, when we're talking ratio test or root test, we want the limit, and then we want to say, how does it look compared to 1? It says this is behaving like an exponential function. Roughly, it behaves like e over 3 to the power k, or to the power n. Now, how does e over 3 relate to 1? Smaller than 1, bigger than 1, something else. It's smaller than 1. Because what is e? Well, there's the chant. Come on, exponentiate. 2.71828. Rah! Yes? Right? You also might know the one for pi. Cosine, secant, tangent, sine, 3.14159. You do not know these things? These are good things to know. Okay, so anyways, e is less than 3. So e over 3 is less than 1. So what's our conclusion? Yes, so this converges by the ratio test. All right. So the work is finding the limit. Okay, how are we doing? Are we ready for another one? Just when you thought you were done. We'll do another one. Well, this one will be a little bit easier. Determine if the sum, 0 to infinity, 7 to the power n, n factorial, times 2n factorial, all divided by 3n factorial, converges. Okay. Well, what test should we use? Of course, trick question because there's only one test we've talked about so far. We're going to use ratio test, but what tells us, if we saw this in the wild, ratio test? Yes. When you see a factorial, ratio test is the option. It's the only option. There's 3 factorials, so triple the fun. Okay, so now that we've had some practice, we can probably do this a little bit faster. We know this is our nth term. This is our a sub n. Everything's positive. We don't have to worry about any negativity yet. So we're going to spend all our effort to do the limit. So rho is the limit. N goes to infinity. A n plus 1 over a n. Okay. So this is the limit. N goes to infinity of, so we're going to do the a n plus 1. Everywhere where we see an n, we're putting an n plus 1. So 7 to the n plus 1, n plus 1 factorial, 2 times n plus 1 factorial, 3 times n plus 1 factorial. So this is our a n plus 1. And then divide by a n, multiply by the reciprocal. 3n, whoops, I don't know why I put that there. It's a very big factorial. 3n factorial, 7 to the n factorial, 2n factorial. So there's the limit we need to take. Okay. So what are we going to do? We're going to channel what we talked about in the last one. When you have a factorial, you can pull off a term. Well, you can pull off as many terms as you want until you can make a comparison. So let's think about what's going to happen. We'll go piece by piece. So thinking about getting to the point where we can do cancellation. 7 to the n plus 1 and 7 to the n, well, that says just break it up. 7 to the n times 7. N plus 1 factorial times n factorial. How much do I want to pull off from this n plus 1 factorial? I want to pull off the first term, n plus 1. Then the next term would be in n, and then I could say, well, just keep going from there, n factorial. Now the next part. This 2n plus 1 factorial is really 2n plus 2 factorial. How much will I pull off? Well, pull off a 2n plus 2. What will be the next term? Well, what comes below 2n plus 2? 2n plus 1. Well, I'm still not down to 2n, so I'm pulling off 2n plus 2, and I'm going to pull off a 2n plus 1, and then what do I have? 2n, and I say, great, that matches, so I'll just write factorial to keep going down. So that 2n plus 2, I'm pulling 2 terms off to get to 2n factorial. Now the 3n factorial we'll leave as is. Downstairs, this is 3n plus 3. So let's start pulling terms off. We pull off the first term. That's 3n plus 3. Okay, now what do we have? 3n plus 2. We need to pull that off. We need to pull off until we get to 3n. So we pull off the 3n plus 2, the next term. And then what do? We got to pull off that 3n plus 1. And then what? And then we're good to go. 3n factorial. So we rewrote that 3n plus 3 factorial by pulling off the first 3 terms. And then we had that 3n factorial in the end. And then we have our 7 to the n factorial, 2n factorial. And now, of course, the satisfying part. We get to start crossing things off. So what goes away? 7 to the n factorial, 2n factorial, and 3n factorial. That's a lot of things. Nice. We like it when we get lots of cancellations. Okay. So this is the limit. As n goes to infinity, what's left? Well, we have a 7, n plus 1, 2n plus 2, 2n plus 1, divide by 3n plus 3, 3n plus 2, and 3n plus 1. Okay, can we take the limit of this? It's a polynomial over a polynomial. That's a good sign. Now there's a couple ways we could do it. We probably could just say, and that is the number, if we're very practiced at it. So here's sort of 2 mindsets. One mindset says, think about multiplying this out. So that if you have polynomial or polynomial leading coefficients. So what would be the leading coefficient upstairs? It'd be 7 times n times 2n, which would be what? 28n cubed plus other stuff. Downstairs, 3n, 3n, 3n. 27n cubed plus other stuff, which is lower order. And then you say compare the highest order terms. What is this going to? 28 over 27. So that's one way to think about it. Here's another option. You can say, hey, let's factor an n out of each one of these pieces. So there will be an n cubed in front, 7. And I factored an n out, so that's 1 plus 1 over n. 2 plus 2 over n. 2 plus 1 over n. Again, factor n cubed out of each term. Then I'll have 3 plus 3 over n. 3 plus 2 over n. And then 3 plus 1 over n. And the n cubes cancel. And now just take the limit. Essentially, everything with this 1 over n goes away. So we get 7 times 1 times 2 times 2 over 3 times 3 times 3, which is 28 over 27. All right, so a couple ways to think about it. But what's our conclusion? What's true about 28 over 27? It's bigger than 1. So since 28 over 27, and it's not bigger than 1 by a lot, but it doesn't have to be bigger than 1 by a lot. Any small bit above 1 tells us that the series diverges. Okay. All right, so that's the ratio test. Any questions? So when you see factorials, you want to get into the habit of ratio test and just the idea of pull off the starts as you need until you're ready to go. Okay, we'll switch now to root test. Very similar idea, so we'll do a much simpler sketch of it. So now instead of looking at ratios, we're looking at roots. That's where it gets its name. The nth root of a sub n. Same conclusions though. Row less than 1, converge. Row bigger than 1, diverges. And row equals 1, no conclusion, for the same reasons. So I'm being a little bit more simple in the explanation. If you're less than 1, well, you can give yourself a little bit of a cushion. Then for large n, you're below rho plus epsilon, which says for large n, you're less than rho plus epsilon to the n. So for the tail, and that's where we care about, the end of the series, the near the infinity part, you're growing like geometric. In fact, you're bounded, really what we should say, by converging geometric series. If you're bigger than 1, again, for large n, you're growing bigger than rho minus epsilon to the n, but rho minus epsilon is above 1. That means you're getting huge diverging nth term test. And if you're equal to 1, it's like you're in a p-series kind of situation. There's ambiguity. You may or may not converge. So there's no conclusion to be drawn. So that's the root test. So let's jump in and do a problem. Does the sum from 1 to infinity of 1.001 to the nth power divide by n to the 1001th power converge or diverge? Now, to give you a sense, when you plug in n equals 1, what's the number that comes out? This one you can do in your head. Plug in n equals 1, you get 1.001. When you plug in n equals 2, you get 0.00000. You have about 300 zeros, and then a 1. When you plug in n equals 3, you have probably closer to 350 zeros and a 1. Like the terms are ridiculously tiny, and they are ridiculously tiny for a very long time. So, does it converge or diverge? Before we work it out, does anyone know what the answer is? And can they quickly say why? It's one of these things where, with practice, you know the answer before you start. Does this converge or diverge? I think I heard a diverge over on this side. It is a diverge. Why? We're comparing two things. What do you have upstairs? Exponential. What do you have downstairs? Polynomial. So it's a race between exponentials and polynomials. And the moral is exponentials will always beat polynomials in the long run. It might take a while, but we'll get there. Okay, so we're going to channel our root test. Why? Because it's right there. Why wouldn't we? So here's our a sub n. Everything's positive. We're being optimistic. Life is good. Okay, so we're going to take our limit, n goes to infinity, of a n to the 1 over n. So that's the limit as n goes to infinity of 1.001 to the nth power, n to the 1001 to the 1 over nth power. Now, if we have a product of a lot of things, and here we do have a product of a lot of things, we just take each individual term to the 1 over nth power. So this is the limit as n goes to infinity of 1.001 to the nth power to the 1 over nth power. And here we have n to the 1001 to the 1 over nth power. What happens upstairs? To take something to the nth, to the 1 over nth, what's that going to be the same as? 1. And spoiler alert, root test is going to be your go-to test for a lot of situations, but if you see lots of things to the nth power, you should be thinking root test. So upstairs you have 1.001. Now downstairs we're going to do something a little interesting. I have n to a power to a power. What's the rule? If I have n to a power, what do I do with those two powers? I can multiply them. But I can also do something else. If I can multiply them, I can swap them. Because in both cases, it's the same thing. It's both 1001 divided by n. Now, why do that? Well, do we know what happens to n to the 1 over nth power? Is there anything that might give us pause for thought and say, we know n to the 1 over n goes to 1. And how do we know that? Well, it is on the formula sheet, but we know it because we proved it earlier. N to the 1 over nth power goes to 1. So when you see an n and a 1 over n, you try to get them right next to each other, because then you can say, n to the 1 over n goes to 1. So we're like, good. So that goes to 1. So if this part goes to 1, then this goes to 1 to the 1001. 1 to the 1001 is also known as 1. So our limit is 1.001. And what's true about 1.001 compared to 1? It's bigger than 1. So this diverges by the root test. So no matter what kind of exponential, even if it's a very small thing, right, just barely over 1, compared to polynomial, that's very big. In the long run, exponential wins. Exponential wins. All right. I have one more problem. We have time. So let's do it. Determine if the sum 1 to infinity arctangent of n to the nth power divided by 2 to the n converges or diverges. Okay. What's the test we're going to use? And why? Root test. Why does root test just seem completely obvious here? Because everything's being raised to the nth power. When you see lots of things being raised to the nth power, that's a good sign. Ratio test would be really confusing here. And so, but root test makes a lot of sense. All right, so we say, great, let's do a root test. So here we have our a sub n. And what do we do? Well, we're going to try to figure out what's the limit, call it rho, as n goes to infinity, a sub n to the 1 over nth power. That's our limit. N goes to infinity of arctangent of n to the nth power divided by 2 to the n to the 1 over n. Well, this simplifies a bit. What does this become? Upstairs, arctangent of n. Downstairs, 2. Okay, so now we say, what happens to this expression as n goes to infinity? What's happening to arctangent? There's this asymptote. Somebody mentioned it. What was it? Pi over 2. So this part is going to pi over 2. So what's the limit? Pi over 2, making it pi fourths. What's true about pi fourths? It's less than 1. Because pi is 3.14159. Remember we said that. Cosine, secant, tangent, sine, 3.14159. So, converge or diverge? Converge. Excellent. Okay, that's it for today.